course. Hello, good afternoon. Hello, can you hear me?
Good afternoon, sir.
Good
Okay,
afternoon. I can.
okay, thank you so much. Is Treasure online? Need to find out. Hello, Treasure. So you're in the meeting. So how do we get the YouTube streaming? You're not able to respond because of noise ever. Yes, can you type? Okay, let me type to you. Okay, okay, that's fine. Okay, that's good. Okay, so can we spend some 5 to 10 minutes to discuss the I'm in class to discuss your experience with the video I sent? Hello? Yeah, you can unmute your microphone and speak. Raise your electronic hand up, you'll be recognized. Okay, Samuel, go ahead. Arugunadi.
Yes, sir. Good afternoon, sir.
Good afternoon.
Yes, sir. I tried to download the emulator yesterday, and I tried running it, but it keeps going back.
What do you mean by keeps going back?
As in, whenever I open it, it will open the first interface, and when I try to click on the example code there, so it brought some examples, and immediately I click that, it will just go back. And if I try opening it back, it is not responding.
Okay, well, that's good. But my question was, I sent a link to a video which I said I recorded from the same class last session to prepare the class for today. I don't know if you saw the video.
Yes, sir.
So yes, I need anyone who saw the video to share his or her experience. Is anybody raising up his or her hand? Okay. So does it mean that nobody saw the video? Okay, so no problem. Okay, so the class yesterday, does anybody have any question? I'm trying to set up to record this class. As I said, it's going to be is a hands-on. I have set up my emulator. So I believe others, you have also set up yours. Okay, so apart from that, does anybody have any other experience with the emulator you were able to download, or you had some issues you couldn't install? Let's take some of this. So I want to start recording, and record button is on now. So, okay. Let me have, can you please indicate if you have any issue with the emulator? It was not, you were not able to install, or you installed, you had some challenge you'd like to share with me? Any? Okay, so do I take it as everybody was, I mean, there is no issue? You can lower your hand. Okay, thank you, Adewale. You can lower your hand somewhere. Arugudade, can you lower your electronic hand? Okay, I'd like to welcome my colleague, Engineer Gbadebo. Okay, so, all right, thank you so much. Thank you, Adewale. Thank you, Buye. Okay, so that's fine. Okay, David Adeyeye, go ahead. Your hand is raised.
It was a mistake, sir.
Oh, okay.
It was a mistake.
All right, so I'm going to share my screen right away. So can you please tell me if you can see my screen?
Yes, sir.
Okay.
We can see it, sir.
Okay. What exactly can you see? Can you tell
see
me?
multiple nested windows, sir.
You can see multiple what?
Yeah, we can now see your screen clearly. We previously saw multiple nested windows, but now we can see
Okay. So, okay, now what do you see now? Tell me what, can you read the title bar? I want to be sure you can see my screen.
Assembler.
EMU.
Okay, so you can see EMU 8086 assembler microprocessor. Okay, so this is the emulator. Once you get it started, it opens up with this, although it came up with something else, something like a dialog box. Okay, let me restart it so that you can see. Okay. Can you see what can you see on the screen now? Hello?
It has been, so we have the desktop view.
Is that all? Can you not locate the EMU 8086 assembler on one side of the screen?
We can locate it, sir.
Okay, so can you find an inner dialog box with welcome in the title bar, EMU 8086 at the center, both emphasized.
Yes, sir.
Microprocessor emulator with integrated assembler version 4.08. Then 1, 2, 3, 4 buttons. The first one new, the second one code example, the third quick start tutor, and then the last recent file. Is that correct?
Yes, sir.
Okay. So if you choose new, it opens up a new work environment. If you click code examples, it opens up a list of sample codes from where you can get started with, from the very simplest code, usually hello world, added to the very, very complex code. Then the third one is quick start tutor. So in case you want to run quick start tutor, so I'm going to recommend that after this class, everybody goes to run quick start. And then the last button is recent file. In recent file, if you click the recent file button, it opens up a list of files that you have opened recently. Then below it is the product registration number, 112. Our advice, if you install yours, please register it to 112. Although at times it doesn't work, you may need to register it to 1131 and 12. Then the website is provided at www.emu886.com. Okay, so I'm going to close this inner box, dialog box, and then maximize my screen. So this is how I got to where we left from. Any question? Is it clear?
So I have a question.
Yes, go ahead. What's your name?
Okay, so my name is Okoli Ogechukwu Aringola.
Okay, good.
So when I opened the emulator, I saw the inner dialog box and you said we should impute 112. And when I clicked on the stuff to include, to put in the stuff, I'm seeing license name and something registration.
Because that was the first time. So that was why I said if you were installing for the first time, I mean, it will require you to register. And to register, simply type 112. If that does not work, register 1112. Okay.
What's the license name?
Use the same information, 1112 or 111, 112, 112. Whatever you use, the same number goes for both.
Okay, sir. Thank you.
So please, can you repeat it? Can you repeat that and confirm if it works?
It works.
Successful. Great.
Yes.
Okay. Any other? Okay, so let's progress. So if you take a look at the desktop, that should be similar. That should be similar to what you have. The title bar presents the name 8086 EMU Assembler Microprocessor Emulator 4.08. Then the menu items, file, edit. In file, you can open new. You find example. You can open existing. You can save as, print, export as HTML. And then you find a list of recent files and then exit. Edit, you can copy and paste, you can cut, select all, find, go to a certain line, indent, outdent, comment a block, uncomment a block, advanced editor macro. So you can do some advanced activity there. Bookmark, you can bookmark, toggle previous, jump to first. All this will be useful during execution. Now, for the assembler, you can compile. Compile simply means that check for errors, but do not execute. You can compile and load into the emulator. You can perform a fast assembler or set output directory. the emulator, you can show emulator or assembled and load into the emulator. That's different from compile. Assemble means that you should execute. No, I mean to assemble into machine code. Compile means to check for error. Then you can do some mathematics, some mathematical operations here. Calculator. Here you find the ASCII code and then help. So these are buttons from some of the activities that we have mentioned. For example, new is from file, open is from file, example is from file, save is from file, compile is from assembler, emulate is from emulator, calculator from maths, converter from maths, and then a whole lot of others, and then help and also. So if you come below, that's the area in which the programming supply your source code, and then the first line is 01 and the cursor appears. So if you check at the bottom of the screen, the line where the line upon which the cursor is line 1, and then the column appears. So for example, the cursor is on line 1 and is on column 4. I'm moving the cursor to the right, then the column is increasing. If I strike enter, you can see that the line number is increasing. And then I can use backspace or delete to erase the lines. Is it clear? Any question? Okay, good. All right. So the next thing is to let me do emulate. I click emulate. Now, what can we achieve with that, or what is currently happening? Whenever you click emulate, it sets the tool or the emulator in an environment where the internal happenings of the CPU is brought to the fore, such that the activities or the execution line after line can be simulated. So now, can you see the inner screen? The inner screen, or rather, not the screen, the inner dialog box described as x86 microprocessor emulator. Can you see? Is it evidence? Thank you. Okay. Now, it also has file, maths, debug. Okay. Does anybody want to ask a question? Let me check. Somebody raise up his hand. Okay. All right. Thank you. Okay. So let's leave those. Now, I want us to focus at the list of registers on the left-hand side. Can you identify the registers there? If you look at these lists, you should be familiar with them. Can you see the list of registers?
Yes, sir.
Okay. And they are as follows: AX, BX, CX, DX.
Accumulate base register.
Then the code segments, IP, instruction pointer, that's what stack segment, stack pointer, base pointer, source index, destination index, data segment, and extra segment. Now, in the 8086 microprocessor, which is the base x86, these are the general purpose registers. Now, the next column presents two blocks of information. The first one is, the first one consists of just one line of numbers. And then these numbers are partitioned into two. The first 4 with a colon and the second 4. Now, if you look at this first 4, can you see 0050 is in hexadecimal, colon 000. What that means is this is the address of the code segment in memory. And if you check, you will find that it tallies with the content of the code segment 0050. So which tells you that in the memory, whatever instruction you give or that is uploaded in your program will be loaded in the segment that starts with 0050. And then the next information is 0000, which means that you are the instruction pointer. That is, this is the instruction 000, like the first instruction. And then which register contains that? The IP instruction pointer. Can you see my pointer, my mouse pointer? 00. So what am I trying to say? Every line of code is identified in the memory by the code segment and the instruction pointer. Very key. And then if you now check within the segment, this is the segment. This is a 64 kilobytes. 64 kilobytes. So if I take it to where we left from, zero. Now, can you see this is now the physical address in memory? 00000. Each information here, each digit is 4 bits. So 4 times 5 is what? 20. So if you remember, I said that the 8086 is able to recognize 1 megabyte of space. That is 2 raised to power 20. So this is the exact location in memory. Location 000. This first 0 is 4 bits, 4 zeros, another 4 zeros. This is now 01015. 0000000, meaning that, so if you convert the whole of this into 20 bits, this is the information that is there. In this case, it says more. Yes, do you have any question? Go ahead. Any question? No. Okay, I proceed.
Yes,
I need
sir.
you to, okay, go ahead. Yes, go ahead.
Yes, sir. I didn't get what you said about the code segment and the IP instruction pointer.
Now, this is what I said, that the code segment presents the address, the starting point in the memory where the code is domiciled. And the code segment here stipulates that it starts from 0050, which is written here, and it also tallies with this. And then the instruction pointer presents the address of the first instruction, because the code segment is a segment of code which contains lines of code, and each line is identified by the IP instruction pointer. So in this case, the instruction pointer is pointing to the first 0000. Now, I went further, I said that this numerics is converted to 20 bits. So what do I mean by that? So this is 0050 colon 000 is now 00500. And what we do is just to add, multiply this code segment by 10 hexadecimal, and then add it to the instruction pointer. That gives you 00500. And then I said each numeric is represented in 4 bits. So 5 numeric times 4 gives 20. So the whole of this information is 20 bits, which tallies with the information I gave in class that the 8086 is able to recognize 20 bits of memory space, and 2 raised to power 20 gives 1 megabyte. So an 8086 processor can only recognize 1 megabyte of memory space. Does that answer your question?
Yes, sir.
Thank you. And then, so if you now check across the information, it says null, meaning that there is nothing written. The memory at this point is empty. The next line is 00501. Then it continues until it gets to F15, and then it then becomes 00510. Is empty. There is nothing in there. So this is the assembly interpretation of what is here. That is, add the content of the BX register. If you check your BX register, it's a 16 bits. So the content of SI register is 0, 16 bits. Add it to the content of the AL register. Remember, I told you that the X registers can be partitioned into 2. So AX being 16 bits can be partitioned into 2 8 bits. So there is the lower 8, which is L, and that is AL, and there's a higher bits order, which is H, that is AH. So in the case of this, it says add the content of the lower A register, which is 0, add it to the, now I need you to be very, very careful here, or to listen carefully. This is not, if you look at the angle bracket here, it says the content of the BX register plus the content of the SI register. Now, where that address points to in memory, that's the meaning of the angle bracket. I need you to listen carefully. It says add the content of AL register 00 to the memory location that corresponds to the BX plus SI. And BX plus SI, BX here contains 00, 16 bits. SI contains 00, 16 bits. Where in the memory? So this is like a variable name. Add 0 in AL to a variable, to the content of a variable location or a placeholder in the memory and keep the result there. I hope that is clear. Do I need to take it again?
Yes, sir.
Yes,
Okay.
sir.
Yes, sir.
Okay. This is an instruction, an 886 assembly instruction made up of mnemonics, 2 operand. The first mnemonics is add, that is add operand 2 to operand 1. Now, operand 2 is a register, the lower order, just 8 bits. It says add it to the angle bracket here, differentiate it from the register itself, but rather this is a reference. For those who do C, this is like a pointer. You know, a pointer is an address of a memory location. So it says that add the content of register AL to an address in memory to a location in memory whose address is equal to the content of the BS register and the SI register. Do I make some sense? Or do I repeat it again? Should I repeat myself?
Yes, sir. Can you take it one more time?
Okay, so let me use my PowerPoint here. Let me use PowerPoint to explain. Can you see my PowerPoint slide? My screen?
Yes, sir.
Okay, that's good. Thank you. Okay, so what I'm trying to say here is no, it's not what I need. Okay, so this is the memory, and I have a location in memory. This. Now look at it says add BX plus SI comma AL, where BX 00 SI equals 00 16 bits and AL 008 bits. So what this means is the address. So this location, the pointer to this address in memory to get the address in memory, is this. The address in memory, that is this location. I don't know what is here. So Finally, what is going to be here is that this location, which is described as bx plus si, will contain 0 plus, I don't know what was there before. Let's assume what was in that location was 1. So that would be 1. I don't know if I made myself a bit clearer. Can you see my screen?
Yes, sir. We are following you, sir.
So what I'm trying to say here is that bx plus si, they are the point. This is a pointer pointing to this location, and then so the content of AL is added to the previous content. So let's assume we're in time t1 now. During time t0, something was there. Something must have been stored in this location, which is described as bx, si. So add 0 to it and keep. So I assume that what was there before time t, so maybe I should just say that, let me just, let me say at time t1, so time t0, the location at time t0, the location bx plus si contained 1. And so at time t1, that is after this line, add bx plus si comma al was must have been executed, what will be left will be so the content of that's bx plus si will now contain 1 plus 0, because al, or let me say plus al, where al contains 0. So it now means that at that point, the content of that memory location after time t1, remember I told you that in digital compute, in a digital processor, execution is based on timing, clock pulse. So I said the microprocessor is synonymous to a blind man, an individual who has challenge with the eye, with the sight, but is able to receive instruction from a clock or from a cue, a system that is able to cue the processor for its activity. Do I make myself clear with this explanation? Can you unmute your microphone and say something? I want to be sure I'm passing across. Am I still on?
Yes, sir.
Yes, sir.
Yes, sir.
Is it clear? Okay, thank you for the reaction. That's good. Adedeji, thank you. So I can proceed. Okay, now, can we now step up a little? You can click on load. Load is simply that the code that is in memory should be, a compiled file or an assembled file should be loaded into the emulator. You can reload for whatever reason an executable file. This is to run a loaded file. It will run it, execute it from start to end. But I like this button for a beginner. Single step. It allows you to step execute. This is like an interpreter. It's similar to interpretation, interpreting line after line. What's the advantage? The advantage is to provide the opportunity to debug or to improve your understanding. But once you are done with the debugging, if you click run, it runs from start to end and then provides you the results. You can change the time in here. Does anybody have any question? Am I clear? Okay, thank you. Thank you. Jayela, thank you. Thank you, Orebi. Okay. All right. So now let's go further down. Let's look at there are some buttons below at the lower end of the emulator dialog box. Screen. If you click screen, it gives you an opportunity to view the output screen. This is like your monitor. If you click source, this takes you back to your program code. You can make modification. You can reset an execution, or you can click on auxiliary. You can check the memory. So this is how the memory is. If you look at the memory, it points us to the CS and the IP, which was what we saw. And then if you check on this line, it supports, yes, somebody's raising up his hand. Is anybody else trying to ask question? Okay, none yet. Okay, that's good. So I was trying to explain that each location in the memory, so this location contains how many, what length of instruction. It starts from 00 to 0010. So it means that this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this is 16 each of 8 bits. 16. And that's why it counts from 00 to 001. So because from 00 to FF, and then it goes back to 1. 00 to FF, it goes to 2. So it counts in base 16. Then you can choose to have this as a list. This is similar to what we saw. Then you can also, we want to see it as a table. So the hexadecimal equivalent, and then you find the ASCII equivalent here. You may want to update it. If you have variables defined in memory, you can check them up here. This will allow you to debug. It gives you at every instance the content of the registers, and then it gives you the code itself equivalent to that line, which says that at this point it's add bx plus cx. The memory reference is a memory reference, comma AL. And then this is the, so in case you're going to, in case you need data is going to be available at the DS here is 00 at line 0000, and what is stored in there is 70H. This is the stack. Remember, I mentioned to you that the stack is a specialized memory area that allows the execution of processes to be done in such a way that whenever there's a transfer from one process to another, there is no loss of data. Before transfer is before an operation is interrupted for another operation, then the information is stacked up so that whenever there is a return to that operation, the information that was stacked is on stack. What do I mean by that? If you flip your mind to your kitchen area, the plate stack or rack in your kitchen, it has one opening at the top and then the bottom is closed. Whenever you place a plate, it goes to the bottom and it fills up. That's a stack. Whenever you need to access the plate at the bottom, what do? You unstack to access and then you return the stack. If you need to insert somewhere along the line, then you unstack, insert, and then restack. The essence is to ensure that no information is lost. You can always trace back from wherever you are to wherever you left from. Then the last one is the flag. Remember, I mentioned to you, the flag are specialized registers that are set to represent action, to account or to give the status of some activities. Carry flag, zero flag, sign flag, overflow flag, parity flag. What is this one? Auxiliary flag. This is analyze flag, and then here is no analyze. What is this one? Interrupt enable flag, and then the last one is
identify that. Because I think I saw something like in the slide that you are using that code. Is there a way you are going to sheet the data segment and the way to?
Sorry, can you take your question again? Sorry, can you take your question again?
All right, sir. Can you hear me, sir?
I can hear you. I want you to take it again.
Okay. So my question is like, how do you identify the code segment and the data segment?
Okay, let me take that.
Like,
Code segment, take it once at a time. Hold on. How do you recognize code segment and data segment? This is the code segment. CS, the register CX, provides you the starting point of the code segment, which is 0050. And then the data segment has location 000. Is that correct? Is that okay?
All right, sir.
Yeah. You're going to, I've not actually written any program yet. I'm still presenting to you the architecture of the hardware. The next step will be to write a simple program, and then I will match the program to the information in the code, the information which I have presented to you in the architecture. So it's always good to start from the architecture and then move on to the code, because we would need to marry the two together. So for now, I've not written any program. I've only been able to identify or present to you the structure, the resources that will be needed during programming. So yes, we're going to need to define the code segment. And what you need to define your code segment is the information in the code segment register. You need to define data segment, and information to do that will be provided in the data segment register. Does that answer your question?
Yes, sir. Thank you very much, sir.
Okay. All right. That's good. Okay, so let's proceed. Thank you for the reaction. Thank you so much. Okay, so I'm going to close the emulator and then try and bring up a simple program. I want to bring up, let's see, a very simple, the usual hello world. Let me find the hello world. Yes, we'll start programming with hello world. Hello world. Okay, so can you see my screen? Hello?
Yes, sir, we can.
Yes, we can, sir.
Okay, so I have a simple program here, which is similar to, which achieves hello world in assembly 8086. If you remember, I mentioned in class that to comment a line, use semicolon. So, and any line that is commented appears in green. So from line 3 to line 28, these are comment statements. Statement provided to illuminate or to provide some information, non-executable instructions. Now, the opening line is name. That is a compiler directive to give information to the user. So it's not an executable instruction. The first instruction appears on line 32. And that instruction is an assembler directive, not an executable instruction. Executable instructions will start with, will be colored in blue. So, and then registers will appear in red, and other operands will appear in black. So from line 32, it says org 100H. What does that mean? It's an instruction to start the programming, the executable instruction, the machine code should be loaded in memory from location 100 hexadecimal. It's optional, you can remove it. It's just to direct where in memory the executable instruction should be positioned. The next line is empty. The next line, 34, is a comment statement which says that set the video mode. Now, what this program does is that it writes to the screen. And to do that, the mode of the screen, the video out must be set. And what is being done here is to set it in text mode. Text mode simply means write 80 characters horizontal by 25 characters. And recognize 16 colors, 8 pages. 8 pages. You will need the registers A. The higher order of A should contain 0. And then the lower order of A should contain 3. Once you set that, and then you evoke an interrupt. Remember in my lecture last week, was it last week? Yes. In chapter 1, I said in assembly language, input output can be performed across all the programming level. You can perform it at the machine level, BIOS level, at the operating system level, or you perform it at the application level. Now, interrupt 10 is at the BIOS level. That is because video signal or operation is an output operation, and so we're instructing the processor to perform an output operation at the BIOS, basic input output. And how do you know that? When you call interrupt 10, that is dedicated to the BIOS. There are quite a number of interrupts. There's interrupt 21, there's interrupt 12. Interrupt 21 is operating system. Interrupt 10 is basic input output system. So what is happening here is that line 35 and line 36 is instructing the processor, the microprocessor, to prepare the video, that is the output screen, for text production. Maximum of 80 characters horizontal, 25 characters vertical. And each character, that makes a total of 80 times 25 makes a total of what? That's about 2,000. You can write maximum of 2,000 characters on a single page. And each character can assume 16 colors. And you can have 8 of such. So once you write move 3 into the lower order of AX. Remember, AX has 2 partitions, high and low. It will move 3 into the low order, that's AL, and then move 0, assume that 0 is in the higher order, and then call interrupt 10. With that, you're about to perform an output to the screen. But what you have to write to the screen has not even been, has not come to play. You're only preparing to write to the output screen. The next line is empty. Line 38 is a comment statement. What does that simply say? That cancel blinking and enable 16 colors. That is, do not blink the characters and enable the 16 colors. To do that, move 1003H to AX. Remember, it was 0003H. I was moved to activate the video screen. Now, to cancel blinking, make it 1003H and move 0 to the BX register and call interrupt 10H. That is still basic input output operation, BIOS operation. Now, the next line is blank, 42. 43 is blank. 44 contains what? Comment statement. Now, here is a segment register. So now define the segment. This is similar to the question one of you asked me. So here, the segment register will now be moved to B800H. Move it into AX, and now move AX into DX. Now, because the target register is data segment, but microprocessor 8086 has a specification. You cannot move an immediate value, that is a constant, into a segment register. Is a violation. The only way you can do it is to go through an intermediary. First, move the constant or the immediate value into a register, and then instruct that the content of the register be moved into the segment value, segment register. What we should have done ordinarily is to say move this constant into DS. It will raise is an error. It's not allowed. So we went through an intermediary, went through AX register, and then move AX into DX. So this is how to set the register. Then we can now instruct what to print. Now, so this is the data part now. The data part. The data segment has been defined. Now we're now decide what should we move into it. So we now say that at location 02H of this data segment, move H into it. This is what? This is a character constant. Then 2 bits after, move P. 2 bits after, move L. And if you go through it, you find out that we are creating this instruction or the information hello world by moving the characters into specified memory location in the data section. Okay, so now let's now get to the color part. So in the color part, there are how many characters? There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 characters, and we intend to manipulate the 12 characters. So remember I said the CX register is good at performing loop counting. So move 12 into the CX register. And then look at the register DX, DI is an index register. We need it to index the memory where we have moved data into. So it now says move 3H. 3H. If you check at location 02H, we moved in H. And at location 04H, we moved in E, because the character is 1 bit. Sorry, it's 1 byte. It's 1 byte. So at location 2, we move in this. So 1 byte, 1 plus 2 gives us 3. That's why it is 3. So the start point for character H of hello world is at location 3H. You now see the intricacies, some of the intricacies in assembly language. You must know exactly where in memory your data is going to reside. Otherwise, you pick the wrong thing. So this is the starting point, and that has been moved into the DX register, destination register, just for indexing. And then 12 has been moved into CX to do what? To ensure that the count, the total number of the iteration. So at this point, it now says move 11101100B into, can you recognize this square bracket, DI square bracket? What it says is similar to what I said earlier on. Who can tell me what is stored in DI, register DI? From the code, can anybody tell me what is stored in register DI? Anybody? Unmute.
3, sir.
Brilliant. So 3H, that is hexadecimal 3. But it now says that hexadecimal 3 is a pointer in the memory. Remember, we have defined the memory DX, and this data have been moved in there. You know, what's stored in 3H is the H character. So it now says move this to that location. And then it says add 2 to DI, meaning that keep skipping this information is a code. The lower parts, 1100, is red, light red color. And then the higher order, 1110, is yellow color. This is to provide coloration. We're going to see it. So move to DI means that you should skip in the video memory and then look to see. So you can now see label. I mentioned label in class yesterday. Label in code segment must be accompanied with a colon. So loop to see. So this is a loop. So it's going to repeat this 12 times. So if you now ask me, what's going to determine the expiration of the loop is CX. A coordinate of CX will determine the expiration. So this loop is going to run 12 times. And then with that, it would have succeeded in moving this character one after the other into the video memory, and then it will show it. So once that is done, it's going to wait, it's going to call interrupt 16H, which is also a BIOS interrupt for inputs. Remember, interrupt 10H, I said BIOS interrupt for video activity. So that's an output interrupt. 16H is an input interrupt, BIOS still, and then it returns. So this is a simple program in assembly to write hello world in two colors, flashing yellow and red. So let's try to, before I'm going to put the class to a close in the next 10 minutes, let's try to execute this program. So to do that, I want to emulate so that we follow the emulation of the execution within the memory, within the architecture. So I have clicked, let me take it again. Emulate. Can you see that? Can you see my screen? I have the emulator, and the program that is running is highword.com. It is .com because it's going to produce a command file because it's org100, and the highword is the name that is going to create for the command file. Remember, at the beginning, let's see our code line. We said name is equal to highword. So now let's look at the code segment to start with. The code segment is 0700, and the first line appears as 0100. That tallies with the instruction pointer. And if you look at the first line is made up of 3 instructions. 3 instructions. These 3 lines of instruction is equivalent to move AX, 0003. Don't try to understand what is studied here, what is stored in here. The most important is to look at the lines, the number of memory locations that will be required to store this. 1, there are 3, there is the command, the operand, and the second operand. And if you look at your code, can you see the code, the source code dialog box, line 35 is highlighted, meaning that that is the first executable line. So if you check a register, at this point, this line has not been executed. So the lower order is still 0. 3 is yet to move in it. So if I step into it, if I click single step, which means execute the first line, and that has been executed. That has been executed. If you check, the A register now contains 03 in the lower order, and the higher order contains 00. And what happens? The next line, the next instruction is the attention here. Interrupt 10H. And interrupt 10H requires 2 lines of memory space to store it. The command and the single operand. If you check your registers, you will find some of the registers containing some information, but the IP contains the address of the next instruction, which is at 01300103, location 01, and that's where it is. So if I step into it, it now transfer instruction to the BIOS. And if you look at that, the BIOS is located at memory location F400. And the processor was able to transfer to the BIOS location with the use of the what? Of the stack segments. So the stack segment has been moved to 0700, and the stack pointer, which is the pointer that identifies the top of the stack, is now FFF8. So if we check the stack here, this is the stack. If you can see I'm trying to bring the stack on the top left corner. This is the stack. Can you see? It's now on location 0700 FFFF8, and it contains 0105, which is an information that has to do with where it came from. So if I step into it, can you now see it has brought up the video output, 80 by 25 characters, 16 colors. If I step further, then it continues. It restored back control to the main program. And what happens? Look at the CS. It has now restored back to 0700 location 015. If you remember, 015 was stored in the stack. So it's now back to where it left from. And at that location, what we have in there, we have, let's look at the source. That is line 39, which says move 1003H into AX, yet to be executed. If I step into it, it executes it. So it becomes, look at your AX, it becomes 1003. And then so the next line is line what in the source code? Line 40, which contains move BX00. Let's look at the BX, it's still 00. If you skip into it, that's good. The next line is to call interrupt 10. So it's going to work alongside with the stack segment. Can you see the stack segment has been evoked, F400, with an IP 0190, which is within the BIOS segment. And then if we look at the stack here at location FFF8 contains 010D. This is where it left from. So after executing this, it's going to return there. So let's continue. Can you see it now? It has now returned to 010D, back to where it came from. So if I continue, it will continue to do that. The process continues. Can you see it has written has successfully written the first character H, because it's writing one after the other. It's going to repeat that. It's writing character E, L. The characters are being written. The characters are being written. If you check the source code, it's now going through the data segment defined here. Hello world, one character at a time, and it's done. It's going to now do what? Color the characters as it's coloring. Foreground in yellow, no, foreground in red, background in yellow. And the section that is responsible for that is this. Look at the looping. Okay. I have gone through this for the purpose of education, training, to allow you to assimilate, grasp it gradually. I do not need to go through all of this. So this is done. Hello world colored. So if I reload it, I can now run it once. Can you see? It just brings it out and it's done. Okay, I want to stop here, take a few questions, and allow you to let's reflect on what we have been able to go through. I know it's a little bit maybe strange, but I'm sure you're going to get by. Yes, Joy Abioye, you're recognized. Thank you, Victor Adewale. Thanks for your reactions. Samson Babatunde, thank you for your reactions. Joy Abioye, you're recognized. Your hand is up. Go ahead.
Okay, good evening, sir.
Good
So my
evening, Joy.
question, we are going to refer back to line 45 of your source code, original source code.
Okay. Line 45.
Yes, sir.
Okay, move AS,
Yes.
B800H.
Yes, sir. So you made a comment on that three sets of code, 3 lines of code. You said you cannot move it directly. And I want to ask if the reason why we cannot move it directly is because you mentioned in class that we cannot move from memory to memory. We can move from
memory to memory. Yes, that's correct. That's good.
Is this an example of not moving from memory to memory?
This is another exception. You cannot move an immediate, a constant. I did not mention this in class. You cannot move a constant, or what I simply describe as immediate value, into any of the segment registers. You are not allowed. The one I mentioned in class, you cannot do memory to memory. I did not mention this. Move an immediate value into a segment register. No, it's not allowed. But there's a way around it. You can move your immediate into a register and then I'll move the content of that register into the segment register, which is what we did in line 45 and line 46.
Okay, thank you, sir. And I also want to request if we can get this assembly flat file just to go through again, sir.
Which assembly flat file is that?
This one that I didn't explain to us.
The hello world?
Yes, sir.
No, it's already in the app. If you install the tool, I got it from the app. That's the very first program in the example. Anyone who has installed MU8086 will find sample programs, and the very first is Hello World. It's written in there.
Okay, sir. Thank you, sir.
You're welcome. Okay. Any other? Okay, David Adedeji. Yes, you're recognized.
Yes, sir. Thank you very much. In one of the lines of the code, like there's there's this that it was commented that we should cancel blinking. So what's the meaning of blinking, sir? Like, what does it mean?
Okay, if we did not cancel blinking, if the characters will be flashing. By design, the character, yes, it was by, without explicitly instructing that blinking should be canceled, characters will appear but will be blinking on and off, on and off, on and off, like a Christmas light.
Okay. And also, sir, can you like shed more light on the interrupts? Like you're talking about, you said we have in 10H, which is the video interrupts.
Yes.
In 16H, which is the input interrupts. Like, do we
Absolutely.
have other interrupts?
Oh, there are so many of them. There are so many. I don't even remember that. Because in the BIOS, various different activities or different BIOS operation, input or output, have been attached to interrupt numbers. So these numbers are what should be evoked or be specified to refer to any of the activity. So there is interrupt 10, there is interrupt 12, there is interrupt 16, interrupt 9 is a long list. I'll send you a file when we get the of interrupts. You need a data sheet. I told you that programming in assembly is like it's electronic. It's like how do I put it? There's no way you can do assembly programming without a good understanding of the architecture. So it's what the designer of the architecture specify, and the developer, the processor developer had specified all of these numbers or figures attached to specific operations or services. So for example, we made use of 2 or 3 here. We have this set video that will be described as interrupt 10 service 3. And I think we also made use of interrupt 16 service 0. Is a long list. So to get a grasp of this, you need to reference the data sheets of the processor, microprocessor Intel 8086. I think I have a document here I can share with you sometimes. I'll do that when you become a bit more comfortable with programming. Okay, David, does that answer your question?
All right, sir. Yes, I thank you very much, sir. And also, lastly, like in the emulator dialogue, like the video you shared with us, like when you in like you have step into. So when you're doing it in the video, like everything was like stepwise. It was like line by line. But yeah, I noticed that let's say when you step into the move, like it's run 3 lines, then into the next one, which was I think. So, I think it was 8, which ran 2 lines. Then the next position that the IP pointed to was like it was not the next line.
You are not audible. You are breaking, so I found it difficult to follow your thought line.
Okay.
The question
Can you hear me now, sir?
Yes, it's still breaking.
Okay, so I said my question is that like in the video you shared with us, like when you were stepping into the like in the embedded dialog, when you're trying to run the code, the program, like it was stepwise. Like let's say you run the move line now, it should go 3 lines. You run out, it go like it should always follow the next line.
Can you type?
Like,
can you type your question? Supply your question in the chat box.
Okay.
Sorry about that. It's not clear. Okay. Any other question? Okay, so let's example. Okay. Can you supply your question in the chat box? I'm waiting for your question. The last was that David? Okay, so in the absence of any, okay, that's good. I noticed that IP was not stepwise. No, IP does not need to. Oh yeah, as in the video shared, there was a point IP jumped. Yes, IP will always jump because every instruction requires different, or that is a different instruction requires different length. For example, move AX, 3 requires 3 instructions. So the next instruction will be +3. So it's going to jump. Interrupt 10H requires 2 lines of instructions. So it will jump in 2s. So do not expect IP to move one line of instruction to humans may not necessarily resolve to one line to the machine. The length of an instruction is a function of its component. If it's a 0 operand, 1 operand, or 2 operands, the size will determine. In fact, even the size of the operand will also determine how much space will be required. It's only you and I who are able to decide or understand a line of instruction as a line of instruction, but for the machine, no. The size occupied by an instruction is a function of the size of its components, the operand and the command. So does that answer your question, David? So do not expect IP to jump piecewise or one at a time. It will always jump based on the direction. For example, when interrupt was evoked, it's completely moved to, in fact, there was no relationship. It went to a different line entirely. And when it was restored, it also went back to where it came from. So we may not be able to relate the information in the IP to the, how do I put it now? So the information in the IP is going to be more of the, as a result of the length of the instruction and whether it is a transfer to an interrupt or to a loop, for example, to a location in the program, and then it returns. So don't get too bothered about that. What you should focus at is what is responsible for the updates of the IP. Does that answer your question, David?
Okay, sir. Thank you, sir.
All right. Any other question?
Well done, sir.
Thank you so much.
Yes, sir.
Okay, Engineer Gbadebo, thank you for your time.
Yes, sir.
So I'm going to, is it a convenient time to close the class?
Yes, sir.
Okay, so I stop recording and I will share the video with Treasure, who is able to chip it into bits and pieces for us. The last virtual class, were you able to, did you receive the files, the video files from Treasure?
Yes, I've got it, sir.
Okay, so I'm processing this one. Treasure will be able to chunk it into pieces It's about 1 hour 30 minutes. I've gotten it now. So I would let me move it into my. So we can stop the class. Thank you so much. So you meet on Thursday. We meet on Thursday for the rest of the class. Thank you so much, and God bless you.
Good evening.
Yeah. Thank you. Thank you so much.
One more.
Yeah, you down.
One more.
I want to just confuse my head.
IPO crazy, bro.
Kí ni Salami ṣe ṣe?
Waiting at the top for there, yo. Crew.
Bàbá gbé fún ilé ẹ̀ kó wá nìkan lọ sùn sí.
Ìwọ náà gbé fóònù lẹ. Ta ló bá sọ̀rọ̀? Ṣé wọ́n tó sọ báyìí? Tí mo tún ṣe fún ọ báyìí, ẹ́? Wetin I do for you?
Praise sọ pé orí ẹ̀ ò pé Praise ló sọ bẹ́ẹ̀ o.
Tó bá bí ẹ̀dá Gáyọ̀ fojú jam wò ó, wà fẹ́. Ìmọ̀ kímọ̀ kò máa gbọ́dọ̀ jọ. Wà fẹ́ ní ẹ̀pà wò ó. Ẹni tó bá dẹrù ọ̀rẹ́ ni ó forí ara rẹ̀ gbé.
Ẹ máa calm down ẹ jọ̀ọ́, ẹ máa calm down.
Ẹlẹ́bẹ̀rẹ̀ ọ̀rọ̀.
Praise dá sọ̀rọ̀ tó wà lẹ́yìn, kí la máa ṣe báyìí? Ṣé fẹ́ràn mi wà bẹ́ẹ̀ ni?
Kí ló fẹ́ kí ló sọ?
Kí ló sọ?
Àwọn èkúrò lórí kìíní ṣó ìṣá.
Mo pé máa lọ nìyà ó.
Mo fẹ́ rárá ìwọ lọ́wọ́ kọ lọ sí mi ò gbà. Mi ò gbà sẹ́. Ó ti lọ. Yeah.